Hello everyone. In this session, we are going to look at yet another problem from CSES problem set, and this comes under the graph algorithm section. So the problem is pretty straightforward. You have you are playing a game, and that game contains n rooms and n tunnels. So and each room has certain number of coins. Okay, like there in every room you have a certain number of coins. You are free to start from any point, or you are free to start from any room, and you are free to go to any room via those tunnels. You have to maximize the number of coins you can collect while moving through the tunnels. Okay, so let's look at example first. Okay, so your first example is you have 4 nodes. Let's say 1, 2, 3 and 4, and you have 4 number of edges also. Those edges are, first is from 1 to 2, second is from 2 to 1, then from 1 to 3, and 1 from 2 to 4. Okay, and you are also given number of coins that are present in the room. In room number 1 you have 4 coins, in room number 2 you have 5, and 3 you have 2, and similarly in 4 you have 7. Okay, now this problem might have been very trivial if you do not have strongly connected components in your graph. So I think you may already have some knowledge about what is a strongly connected component. So strongly connected component is a component in graph where you can travel from any node to any node of that component. Like here, if you look at 1 and 2, you can go from 1 to 2, as well you can go from 2 to 1. Okay, so if there were no strongly connected component in the graph, like the graph would only have been like this, then don't you think this question is so trivial? You just start from anywhere you want. Like let's say you start from 1, and coins were 4, 5, 7 and 2. Let's say you start from 1. Now you have choice to go to either 2 or 3. So you will ask 2, hey 2, what will be the maximum number of coin I would get if I go to you? And similarly you would ask 3, hey 3, what would be the maximum number of coin I can get if I go to you? Okay, so let's say 2 said you will get 100 coins if you come to me, and 3 said you will get 200 coins if you come to me. Then definitely we are going to choose 3. Okay, these are not the actual figure 100 and 200. I am just taking arbitrary values. So you know what to do. You just ask every node. You just go to every node and ask all of their children and take out the maximum one. Take out the maximum children, maximum one. Take out that children which gives you maximum number of coins, and go to that path and ignore rest of the paths. But the problem arises, like this is very trivial. This is not any. I don't think there should be any confusion regarding this question if you have not any strongly connected component. But problem arises when graph contains a strongly connected component. Like here you can go from 1 to 2 and as well as 1 to 3. Okay, as well as you can go from 1 to 2, then go from 2 to 1, then again go from 1 to 3. So in this question you can go from 1 to both 2 and 3. So you are not just taking out the maximum, you can take even both, or maybe there is a third person also. So you can take all the 3, or maybe you will only take the third one, if it has very high number of coins, like let's say 500 coins, so even sum of 2 and 3 are not getting you to what 3 alone, what this room alone can provide you. So in this case you can't apply the maximum rule, like you just go to the maximum children. You can go to all the children, you can go to some number of children, you can avoid some number of children. So this kind of problem arises when you figure out, when you deal with strongly connected component. Okay, so how to deal with it? So what intuition we can get is, if there is a strongly connected component in the graph, then it is definitely that I can cover every node of that component. So instead of making the whole component as number of nodes or as collection of nodes, why can't I represent the whole component as a single node? Okay, like if here is 1 and 2, then why can't I represent this only as 1? And what the value that 1 will contain in itself? It will contain both the sum from previous one and previous 2. So now 1 contains value of 9. Okay, and this is pure logical. You are not like making any hypothesis or making any assumption. This is pure logical. You can go from any node to any node of any strongly connected component. So let's say there are even more number of components there, then you can go to every component, add all the values that they provide, and represent it just by a single node. Okay, now rest of the things that were not in part of strongly connected component, they will remain the same. So now this problem becomes the problem of this type, where you do not have any strongly connected component. When you will resolve, let's say here also you have some components that are strongly connected to each other, you also resolve this, like you will resolve every strongly connected component of your graph and convert it in a new graph, where there are no strongly connected components. Then this question is exactly similar to what we have discussed earlier. Now you can go to 1 and ask all of children, hey, which one is providing you more value? Here 4 is providing you more value than 3, so you will take 4, and your total answer would be 9 plus 7, that is 16. Okay, so I think this is all the intuition part. Okay, so now let's start first of all how to find strongly connected components. You all know there is an algorithm called as Poisson-Rajou algorithm. So I am not going to discuss the Poisson-Rajou algorithm here. You may refer to any website like CP algorithms and all. Okay. And what you have to do, let's say you have found out that 1 and 2 are in a component. Then how will you decide to represent the component? So for this you have to use disjoint set union, or you have studied about union find data structure. You have to use disjoint set union. All the nodes in a strongly connected component will be having union into one node. Okay. So now I think you are quite able to code it up, but again I am showing you my code. Okay, so let's go to my code. So what I have done here, let's go to first main function. Okay, so I have taken the input of n and m, I have taken the input of coins. Okay, I have made the original graph. Since graph is directed, then you can only push back v into u and not the vice versa. Then I made a class of DSU. I think you already know how to make class of DSU. Here here is your DSU class. You have a constructor. Inside the constructor you are initializing parent and rank vector. You will initialize parent to itself. Then if you have any find operation, then you can do this stuff. I think you already know how to do find and union in disjoint set union. If you have any type of confusion, then you can refer to any other YouTube video or any other articles on the internet. Now after declaring the DSU class, what I am doing is I am making all the connected components, all the strongly connected components using Kosa-Raju algorithm. Here I am passing my graph and DSU. What I am doing is, firstly, I think you know there are two DFS calls. First we find the order of DFS, then according to the order of DFS we again do a DFS. Okay, so and then we transpose the graph on the basis of order of ending time of DFS. Then what I am doing, if two components are in the same strongly, if two nodes are in the same strongly connected components, then I am unioning it. Like I am doing the union of all the nodes. Okay, so after doing this Kosa-Raju's thing, I will get all my nodes in a strongly connected components represented by a single node. Okay, now I have to also sum up all the values. Like if there are two nodes in strongly connected component, then when I am representing those two nodes by only a single node, then I have to make sure that the value of single node, number of coins in that single node, is the sum of all the coins of coins of all the nodes. Okay, so I am traversing in the graph, and I am finding the parent of every node, and I am incrementing the value of parent by number of coins that node contains. So by doing this, I will have all the nodes, I will have sum of all the coins in just a single node. Okay, now I am making another graph, new graph. Like if I have represented all the strongly connected components into single nodes, then our graph will have changed. So how am I making a new graph? Ignore this line, this is just a debug function. Okay, how am I making a new graph? I am traversing to every node of the original graph and going to every edge of original graph. I am finding the parent of both the node. Like earlier, if 1 and 2 were connected, then I am finding the parent of 1 as well as parent of 2. If both the parents are equal, then both the graphs are in a single connected component, or both the nodes are only represented by a single node. So there is no need to add edge between those two components, because they are converted into single node, and those two nodes no longer exist. Only a single representative node exists for those two. So I will just continue if both are equal. If not, then I will make an edge from xx to yy. Okay, now what I am doing is I am making a set of new nodes. What is new nodes? New nodes are all the representational nodes that are left in our new graph. Like most of the nodes were merged into single node, then all those single nodes are inside the new node set. How am I making the new node set? I am going to every node of the graph and I am just inserting their parents. So since I am making set, then only unique characters or only the parents are going to into sets and a single time. Okay, so I will get all the new nodes of our graph. Then what I'm doing, then I'm doing just a trivial thing, just a trivial dp on graph that you already have done if the graph does not contain a strongly connected component. Now the graph contains, now our graph, the new graph that we had made is free of any strongly connected components, so we can just apply our normal dp. So what will I do? I will go to every node of new node. I will go to every node of new node. If that node is not already visited, then I will find the maximum number of coins that I can collect from that node and just return the answer. So let's see how dp function is working. So here is my dp function. I have passed our new graph. I have passed the current node that I am visiting. I have passed the new values vector. What is new values vector? New values vector contains all the contains number of coins on single representational nodes. Like if there are 10 nodes in a strongly connected component, then sum of all the coins on those rooms will be in new values vector and a vector visited. Okay. If dp of node is not equal to -1, although I am not doing DFS, so there is no point of visited and everything, I am just doing it in a dp, so it will just go in order of n. So if dp of node is not equal to -1, it means we have already calculated the answer for dp of node. Then I will just return dp of node. Then else what I am going to do, I am initializing our current answer as new values of node. Like if I am at index 1 and I know there are 9 coins in first room, then I will start our answer from 9. Then I will go to all the children of new graph, not the original graph. I will go to all the children of new graph and find out the maximum one. Whichever gives me the maximum one, I will add that to my answer and return that. Okay. So in just one dp traversal, you can have all the nodes that are all the number of points that you can get by visiting those nodes. Okay, so from here what I am doing, I am going to every node that are not visited, or just I am not since updating visited vector, so you can just ignore this. I am going to all the nodes and finding the maximum answer. You can say, okay, you are going to all the nodes and you are doing f function. So going into all the nodes in worst case may take order of n times, and f function will singly take order of n times, so it is order of n square. But it is not, because in maximum you can make you can make any node visited only one times. You can just visit a node and mark its dp. Its dp of node will become not equal to -1. Then let's say you first searched for node number 1. You marked node number 1, node number 3, node number 4, and all those dp becomes not equal to -1. Then whenever you go to node number 3, 4, or all those nodes that have already visited before, then you just not need to go here anymore. You will just return from here, because dp of that node has already been found out. So this is not order of n square, this is order of n only. I think you all may now think about it. Okay, at last I will just return our answer, and this is it. So once again I am just revising the whole story. So the question was very trivial. If we didn't have strongly connected component, if we had the strongly connected component, we just make them all represented by a single node, make the whole strongly connected component represented by a single node, and via using DSU and just how to find strongly connected component, we have the Kosa-Raju algorithm, and then we are just using our normal trivial DP function for a graph when there is no strongly connected component. Okay, so this was from my side. Thank you. We will meet in the next set of lectures. Okay, bye.